Now we will proceed to measure the spectral responsivity in EQE of this monocrystalline silicon device. The device has front and rear contacts, so we can use the temperature controlled vacuum mount, and it is a silicon material semiconductor which will respond to the 580 Hz of the transformer mode, and being the preferred mode of measurement, we shall go forward and measure in the 474 transformer configuration.
So now, ensuring that all of the elements of the PV300 system are powered on and connected to the computer via USB as required, we shall run BEMN Plus from the desktop and initialize in the 474 transformer mode by double-clicking. The system initialization process will move the turret and the filter wheel in the monochromator to a fixed reference point, and also move the motorized stages to its reference position. Now, first we need to make sure that we calibrate the system. We should place the detector, the reference detector, under the beam, and it's also useful to let some light be transmitted from the monochromator to ensure that the beam is aligned with the detector. In the specific case of the PV300XY, we must control the position of the detector using the XY stage utility. In a standard PV300 unit, we can simply move physically the detector mounted atop the detector point on the temperature controlled vacuum mount under the beam. In the motorized XY stage utility, a relative detector location has already been defined, and we will go to that position. The detector mount position will be taken under the beam. We have yet to mount the reference diode. And in terms of setting the monochromator to a wavelength at which to view the monochromatic probe, we will set it to 555 nanometers, the peak of the visible region, a nice green color. So we can close that, and now we will go and place the reference diode under the beam.
So we have now to place the reference diode under the beam of the PV300. We must also make sure that the divert mirror at the top of the PV300 chamber here is moved to the left position, thereby allowing light to transmit to the temperature controlled vacuum mount and reference diode. One simply turns the thumb screw by a quarter of a turn to translate across, and then fix back in place. We can connect the reference diode to the transformer using the thick ENC cable provided, and of course we should just fix the thumb screw to the side of the detector to hold it in place. Now we are ready to perform a calibration measurement.
So the doors of the PV300 have been closed, and we can come into BEMN Plus to launch a scan. We can define this through either scan setup, or we can follow the scan setup icon. Now, typically during calibration, I would recommend performing 3 scans of each reference detector. 3 gives one confidence that this measurement is stable, and this is important since the calibration through the calibration factor will figure through all of your measurements. If there is some noise, for example, in the calibration measurements, that will be seen as an artifact in all future measurements. And for now we will only select 1 scan. The silicon reference device can be used over the range 300 to 1100 nanometers, over which we will scan for the present. It's good to check in advance that data correction is not selected. Data correction signals that the system is calibrated, which clearly when we're calibrating the system should not be the case. And we will hit New Scan. At all times during system calibration, the y-axis should read signal in nanoamps. The zero calibrate procedure places a shutter at the exit of the monochromator, allowing no light to the detector, and takes some offsets of the system. We will pick this scan up at the end of the measurement. Now we have come to the end of this measurement, we can save the file. This leads us to the Bentham Plus Spectra folder, where we can define the name of the file, making some reference to what we are measuring, the silicon calibration device, for example, and say, for example, today's date. Of course, you will define your own naming system. You can close that and close that. In order to apply data correction to calibrate the system, we should go to Scan, Data Correction. The certificate file is the calibrated data in amps per watt of the device that we're using to calibrate the system with, and it is this DHSI silicon photodiode with the same serial number. The system file is how we have measured our system with this detector, i.e. the file we have just saved. We can hit Calculate Calibration Data to generate the calibration factors. Data correction is not selected. Do you wish to select now? Yes, we do. And save to file, and we can save it as the SI calibration and perhaps today's date. Now we can return to scan setup. We will see in advance that data correction is now selected, and we can go ahead and measure the device with calibration in place, so reporting units of spectral responsivity.
The silicon reference diode was calibrated 300 to 1100 nanometers, and the germanium reference diode 800 to 1800 nanometers. Wherever one wants to measure a sample over a range that extends beyond the spectral range of one or the other detectors, we have to calibrate with both detectors. So we've calibrated the system presently 300 to 1100 nanometers with the silicon photodiode. So we'll remove that and in its stead place the germanium photodiode to allow us to measure our device up to 1200 nanometers just beyond the band edge. So we'll hold the device in place, connect to the transformer and return to perform a measurement.
So now we will calibrate the system with a germanium photodiode over the range 800 nanometers, the minimum wavelength for the germanium diode, to the 1200 nanometers to which we want to measure our device under test. So we select 800 to 1200 nanometers, ensure again that data correction is not selected, and perform our new scan. Now we've reached the end of the measurement of the germanium reference device. So we shall save to file, giving an appropriate name. Let's call it the GE Cal of today's date, and we can close those windows. In order to implement a calibration consisting of two parts from two detectors, the silicon and germanium devices, we should use Utilities Correction Calculator. This utility will perform from the two separate calibration factors one single that can be loaded in the Bevan Plus data correction page. So we take Spectrum 1, Spectrum 2. Spectrum 1, let's take as the silicon device. The scan is our measurement of the silicon reference diode, and the certificate is the calibrated responsivity of the same device. In Spectrum 2 we shall take as our germanium measurement, and the certificate is the certificate of the same device. We can load the germanium as Spectrum 1, silicon as Spectrum 2, there's no import there. What is important is which absolute spectrum we take. Now, the utility works in the principle that we seek a continuous calibration factor, clearly. We don't want any discontinuities in that. Where there is a discontinuity between the two factors, we shall scale one with respect to another. So that which we do not scale, the absolute one, we take as the silicon device at all times. The reason for that is that the silicon device is a 10 by 10 chip compared to the 5mm diameter germanium device. So it is more likely that the monochromatic probe would be fully measured by the silicon device than germanium device. And of course that depends on the size of the monochromatic probe used. In most cases there'll be very little difference. So the absolute spectrum is that of the silicon, and we show overlap. And we can see here the ratio in green of the two calibration factors, the calibration factors being shown here in red and blue. We tend to automatically choose a 950 nanometer crossover wavelength. That is to say that we will take the silicon data from 300 to 950 nanometers, and thereafter we'll use the germanium data. In that manner we also avoid the band edge region of the silicon device, which has of course an inherent temperature dependence. We shall save to correction file, maybe calling it SI GE cal, and today's date. I say OK, and we can close this window, no need to save. Two last steps. In scan data correction, we should load from file the silicon germanium calibration we have just generated. Data correction is not selected. Do you wish to select it now? Yes. And finally, of course, we should change the scan range in BEM Plus as we require for the full spectral range 300 to 1200 nanometers now. In advanced, data correction is selected. So we are ready now to put our device under test in place. In utilities, XY stage utility, we can move the motorized stage to the middle location where the sample is positioned and hit go. And we can also set again to monitor the monochromatic probe at 555 nanometers to view the probe with respect to the sample. And we'll input 555 now that the stages have reached their location and hit go.
Now we will set up our device under test to measure its spectral responsivity. First, I will illuminate the VCTE20 unit and switch on the vacuum supply to hold the sample in place. And we should position the sample in such a manner that the monochromatic probe is not illuminating either the electrodes or the fingers of the device. With this top rear contact device, we can use a single probe to electrically connect to the device. So I position the probe on the right side of the temperature controlled vacuum mount. We connect the back plane of the mount using the mounting point to the rear and connect that to the mounting point on the probe. We can gently loosen the clamp of the probe and lower into position, locking it in place and also locking in the magnetic base in place. We should use the small pennies to block up the vacuum points which we are not using to obtain a better electrical contact to the temperature controlled vacuum mount. Not only good, better electrical contact, but also better thermal contact, of course. Finally, we should connect the output of the probe by the thick BNC cable to the transformer input, and now we are ready to measure the device.
So we're now ready to launch a spectral responsivity measurement of our silicon device over the range 300 to 1200 nanometers. Now, as we have highlighted before, we typically perform measurements of spectral responsivity of photovoltaic devices under one sun bias, and at this point we can illuminate the light bias. In utilities, we have the PV bias control, which allows us to bias the source on and off as required. So now the light bias is on, we can perform a new scan of the device. We see on the y-axis detector responsivity being reported, a calibrated measurement, and we will look at the results at the end of the scan. We have now come to the end of the measurement of our silicon device under test. We can save this file or mSi cell, for example, and give today's date for some reference. You can close this window. From this view of detector responsivity, we can go to analysis quantum efficiency to directly evaluate the external quantum efficiency of the device, and we can toggle back to detector responsivity as required.